In 1915, Albert Einstein revolutionized our understanding of gravity with his general theory of relativity. One of its most astonishing predictions? That space itself could collapse under extreme mass, forming an object so dense that nothing, not even light, could escape. A black hole. For decades, it seemed like pure theory. Many scientists still weren't sure black holes were real, and even Einstein himself doubted whether his math would actually translate to reality. But it did. And we now have conclusive evidence that black holes exist, just like Einstein's equations predicted they would. Black holes are some of the strangest and most extreme objects in the universe. They're invisible, yet powerful enough to pull in stars and bend light itself. And while no one's ever fallen into a black hole to tell the tale and describe it to us, scientists have a pretty good idea of what might happen if we were to get close to one. In this lesson, we're going to explore that mystery and learn the science behind the science fiction lore of black holes. Just a warning, it might get a little weird, so buckle up and try not to fall in as we get close to these cosmic thrillers. What is a black hole actually made of? At the very center of a black hole lies something called the singularity. This is a single point that contains all the crushed mass of the black hole. It's incredibly dense, so dense that the normal laws of physics as we know them seem to break down. Scientists aren't even sure what really happens there. It's like nature's ultimate case of, we don't know yet. Surrounding the singularity is the event horizon, the boundary of the black hole beyond which nothing can escape. Think of it as the point of no return. If you cross this invisible line, you're not coming back. Not you, not a spaceship, not even light. That's why it's called a black hole, because once light goes in, it can't get out. But if light can't get out, then how do we see a black hole, since light is what our eyes are capable of detecting? In your lesson activities, you'll explore this question further. But what we can see is the matter orbiting and sometimes being absorbed by the black hole. If your orbit doesn't have enough velocity, you may find yourself spiraling closer and closer to the event horizon. And because of this, many black holes are surrounded by an accretion disk, a swirling, glowing ring of gas, dust, and even entire stars that are being slowly drawn toward the event horizon. As this material spirals closer, it heats up and shines incredibly brightly, sometimes outshining entire galaxies. So even though the black hole itself is dark, the chaos around it can be brilliant. Some black holes may also have relativistic jets, narrow beams of high-energy particles shooting out from the regions around the black hole. These jets can stretch for thousands of light years, and we're still learning exactly how they form. But no two black holes are identical. And because of this, scientists have come up with a way to classify black holes and group ones with similar characteristics. Let's take a look. Let's start with the most common type of black hole, the stellar mass black hole. These form when massive stars, at least 20 times the mass of our sun, reach the end of their lives and explode in a supernova. What's left behind is a dense core that collapses under its own gravity into a black hole. These types of black holes can be found sprinkled throughout every galaxy in the universe. The stars that form these black holes are many times larger than our sun. But how big is the black hole itself once it forms? Probably not as big as you might assume. The smallest black holes may only be around 40 miles across, which means that a black hole would fit on the island of Oahu, Hawaii. However, what they lack in size, they make up for in mass. The singularity may have a mass that is 20 to 30 times the mass of our sun. This is what causes the immense density of a black hole. And this extreme density gives rise to the unimaginably high gravitational force surrounding the singularity. But remember that stellar mass black holes are only the smallest variety. Larger black holes, known as intermediate mass black holes, might weigh in at hundreds or thousands of solar masses. Recent evidence, like unusual X-ray emissions and gravitational wave events, suggests that these behemoths can be found in dense star clusters, or forming from smaller black holes merging together. And then there are the supermassive black holes, the true giants. These monsters can be millions or billions of times more massive than our sun. Almost every large galaxy has one at its center, including our own Milky Way. Scientists still aren't exactly sure how these supermassive black holes formed. Did they start small and grow by consuming more stars and other black holes? Or did they form in the early universe from giant clouds collapsing all at once? These are some of the burning questions of cosmology today. The supermassive black hole at our galactic core is called Sagittarius A. And while it's over 4 million times more massive than the Sun, it's also over 26,000 light years away. Thankfully. Why is the gravitational force around a black hole so immense? The simple answer is that a black hole has a lot of mass. But why does that cause its gravity to be so extreme that it can even trap light? What does mass have to do with gravity? Do you remember learning about Einstein's theory of relativity earlier in the course? He described gravity not as a force in the traditional sense, but as the bending of space-time caused by mass. Picture a stretched out sheet of fabric. Now, place a heavy object in the center. What happens? The fabric dips. If another object tries to move past it, it instead spirals inward because it's following the curve of the fabric. How do you think this view of gravity helped Einstein arrive at the prediction of a black hole's existence? What will happen to the fabric of space-time as the object at the center becomes more and more massive? Pause the video for a moment and see if you can make a prediction about how this change could cause a situation where nothing can get out of the black hole. As the mass of an object increases, it warps space-time more and more dramatically, like pressing deeper into that stretched fabric. If enough mass is packed into a small enough space, the curve becomes so steep that it forms a kind of bottomless pit in space-time. This is what we call a black hole. Once something crosses the edge of that pit, the walls are too steep. Not even light is fast enough to climb out. What would happen if you approached a black hole? Do you think you could get right up to the edge and stay safe? Let's imagine it. You're in a spacesuit, hovering near the event horizon. If you dive in feet first, gravity at your feet would be immensely stronger than at your head. This is due to tidal forces, which arise due to a difference in gravity between 2 points. It's just like the tidal forces from the moon that cause our ocean tides. Normally, to experience tidal forces, the 2 points would need to be really far apart, like opposite sides of the Earth. But because the gravity near a black hole is so immense and changes so quickly with each millimeter, even the 5-foot distance between your head and feet can mean huge shifts in gravity. What does this mean for your body? After all, it's going to experience gravity at your feet that is millions of times stronger than the gravity at your head. Quite simply, your body would be stretched, dramatically stretched. Astronomers call this effect spaghettification. And yes, that's a real word. You'd be stretched into a long, thin strand of atoms as you're pulled toward the singularity. From your perspective, it might all happen quickly. But to an outside observer who stayed a safe distance away, you'd appear to slow down and eventually freeze in place. This bizarre split in how time is experienced, yours versus someone else's, is one of the mind-bending consequences of warped space-time near black holes. It's an effect known as time dilation. Time dilation is the difference in the rate at which time passes for 2 observers based on the gravitational force they are experiencing. Basically, it means that Time doesn't tick at the same rate everywhere in the universe. Near a black hole, this effect becomes extreme. So as you fall toward the event horizon, time feels totally normal to you. You blink, you breathe, seconds pass as usual. But to the observer farther away, those same seconds might take hours, days, even centuries to unfold. Eventually, it would look like you had stopped moving altogether. And it's not just science fiction. Time dilation has been confirmed through both theory and experiment. Time really does tick more slowly in stronger gravitational fields, and black holes are the ultimate example. They don't just bend space, they stretch and twist time itself. I did warn you that it was going to get weird, and this is about as weird as it gets. Well, on that fun note, we're going to sign off for today. Next time you hear about a black hole, think about the laws of physics that make them possible, and be very glad there's not one near us. I'm Caroline, and I'll see you next time.
Hey, hey.